What is a curve? Intuitively, we think of a curve as something that we draw like this. Starting at one point, we just draw, and we can draw in any direction, and we've got a curve. How can we formalize that and describe a curve mathematically? Well, watch as I draw a curve and follow just the x-coordinate of the points that are shown. If you think of a time variable t, the function that describes the x-coordinate of my point at time t, we'll just call f of t. And if we think of the same thing, again, follow the y-coordinate of my point at time t, we'll call the function that describes the y-coordinate g of t. When we put those together, we get what we call a parametric description of the curve. X equals f of t, y equals g of t, and the value of t, think of that again as a time variable, though it doesn't necessarily have to be. The values of t begin at some point, let's say that's a, and end at some other point, that's b. So again, I'm going to draw the curve. I know these curves aren't exactly the same each time. Here's a curve. This will be where I start. That's the point, actually, that's the point here, f of a, g of a, where I began the curve, and my ending point is the point f of b, g of b. I would like to show you some basic curves which we can parameterize rather easily, and which will be helpful if you become comfortable with their parameterizations. Here we have the unit circle, a circle of radius 1, centered at the origin. We can parameterize this curve very simply in the following way. X could be cosine t, and y can be sine t. And here we're going to have t running from 0 to 2 pi. Notice that when t equals 0, x is 1 and y is 0. So we're going to begin at this point here, the point 1, 0 in the plane. And as we increase t, we're going to be moving around the curve in this direction. Here's the point when t equals pi over 2. X will be 0, y will be 1. Let me put it here. T equals 0 here. When we keep going in that direction, we get to the point here where t equals pi. Down here we'll get to t equals 3 pi over 2. And then we'll be back at this same point where we started, where t equals 2 pi. So we provided here a parameterization for the curve that begins and ends at the point 1, 0. This point here in the plane here. The curve begins and ends there and moves around the circle in the counterclockwise direction. Now we could parameterize the curve differently and run in the clockwise direction by giving it a different parameterization. Let's say we had x equals cosine t and y equals minus sine t. Again, we'll have t going from 0 to 2 pi. Again, when t equals 0, we're right here at this point, the same beginning point. But now as we increase t, we get down here when t equals pi over 2. With this new parameterization, we're back here when t equals pi. And we're up to here when t equals 3 pi over 2. And back to here when t equals 2 pi. So that just gives us a parameterization for the same curve going in the opposite direction. There are many different parameterizations we can give for the exact same curve. Let me show you one more here. We could have x equals cosine of 2t and y equals sine of 2t, but now we'll have t running just from 0 to pi. And this is like the first parameterization. It will start at the same point. It will move around counterclockwise. But now we'll get here, I'll use the term more quickly, when t equals only pi over 4, then the 2t here will be pi over 2, so we'll be at the point 0, 1. And then we'll get here when t equals pi over 2, we'll get down here at the bottom when t equals 3 pi over 4, and we'll get back to the starting point when t equals pi. There are always going to be many, many different ways one could parameterize the same curve. Often you'll want to find a simple parameterization, and if we're thinking of t as a time variable, the parameterization won't just tell you what the curve is, but it'll indicate motion along the curve from the beginning point to the end point. Here's some variants, other curves that we should be able to parameterize. Let's say we want to talk about a circle of radius r centered at the point 0, 0 at the origin. This will have a simple parameterization. X equals r cosine t, y equals r sine t, and again here we'll have t going from 0 to 2 pi. Remember, parameterization always requires that you give me functions for x and y, and you give me an interval. In this case, we're always going to be talking about a closed interval for a parameter t. So here we have a circle of radius r, and we're going to be starting at this point, the point 0r. I'm sorry, the point r0, and move along counterclockwise in this parameterization. This parameterization of the circle is just like the first parameterization we saw for the unit circle, but we've just scaled everything up by this factor of r here for both the x and y coordinates. If we want to talk about a circle with a different center, say the center of the circle is the point AB, and again we have a radius which we'll call r. Is there a simple way to parameterize this? Yes, we just take the parameterization for the circle that we saw in the previous slide, and we shift everything to have it centered at the new point AB. So we'll use x equals a plus r cosine t, and y equals b plus r sine t. Again, t will run from 0 to 2 pi. What about a line segment like this? If we're starting at the point 0, 0, and we're going to the point AB here, how can we parameterize that? Well, again, there are always going to be many ways to do it. Here's probably the simplest. We can just let x be at and y be bt, and here we'll have the parameter t running from 0 to 1. You can see easily that when t equals 0, we're at the point 0, 0, which is the origin. This will be our beginning point. And when t equals 1, we're at the point AB, and it should be pretty clear that for any value of t in between the two, we're at a point somewhere on this line segment between the origin and the point AB. We can do a similar thing if we just want to parameterize any line segment. Let's say we have a line segment from the point AB to the point CD. We can just let x be a plus, now here's the slightly tricky part, how far over do we want x to go? The difference in the x-coordinates is c minus a, so I'm going to add c minus a times t. Similarly, y will be b plus d minus b times t. And again, we'll run t from 0 to 1. You can see easily that when t equals 0, we're at the point AB here. That's our beginning point for the curve. And when t equals 1, we end up exactly at the point CD. And we trace out exactly this line segment moving in this direction here. I want to talk about going backwards. Let's say somebody gives you the parameterization. You'll see here we have the parameterization for the circle we looked at earlier, a circle whose center is the point AB and whose radius is R. How can we eliminate the parameter, which means find an equation involving x and y, which will describe the curve? Well, what we're going to do first, the idea behind eliminating the parameter is somehow just derive this relationship between x and y that doesn't depend on t anymore. One way to do this, though you can play around algebraically and often find many others, is notice here that x minus a is r cosine t. So if we square that, x minus a squared is r squared cosine squared t. We can see that we'll get a similar thing for y minus b squared. That will be r squared sine squared t. And then we see there's this great relationship between cosine squared t and sine squared t, that their sum is always 1. So then when we add x minus a squared plus y minus b squared, what we get is exactly r squared times the quantity cosine squared t plus sine squared t, which is just r squared. So in the end, we get x minus a squared plus y minus b squared equals r squared, which you can all recognize as just the equation for a circle of radius r centered at the point AB. Let's see how that looks when we eliminate the parameter for this curve, which you should recognize again from earlier. How can we eliminate the parameter here? Well, there's a nice trick here that if we look at the first equation, we can write x minus a divided by c minus a, we get t. That's just solving the first for t. If we solve the second equation for t, we get t equals y minus b over d minus b. Putting those together, we just get x minus a over c minus a equals y minus b over d minus b. And this might look a bit messy, but you can recognize this as the equation for a line. The line certainly will go through the point AB, and if you check carefully, you'll see that if you put in the point CD as well, the two equations are again satisfied. Notice that for this to make any sense, we'll need A not equal to C and B not equal to D, so that the points are different points and not on the same horizontal or vertical line. This will be the equation, just a single linear equation involving x and y. It will be the equation of a line, and it will be the line that contains the line segment. Now notice that this equation contains the line segment. To determine the beginning and ending points, we really need to remember we don't get the entire line, we just get that one segment from the point AB to the point CD, because we're only allowing the parameter t to run from 0 to 1.